using atomistic simulations and continuum theories. Is my voice okay, clear? Louder, okay. Today, considering the topic of the course, which is structural masonry and my little experience in nanotechnology, we are going to talk about a multidisciplinary topic, which is the application of nanotechnology or nanomaterials for conservation or restoration of cultural heritage. Okay, in the picture that you could see some actually symbolic nanoparticles. And here is also a part of a very famous monument in Iran named Persepolis, which is actually near my birth city. And I have also found this introduction movie interesting for this. Okay, in this short video, you could see the overview of the building, and you could also have an estimate of the size considering the people walking around. It is built in 500 BC, and this one is actually, unfortunately, just a virtual restoration of Persepolis. The real function of this building is actually not known, but it was probably for celebration of Nowruz, which is the beginning year of Persian year at the beginning of a spring. And unfortunately, this building was burnt during the war at 300 BC. And this is the burning of them. Okay. What?
When?
300 before Christ. I mean, it was actually the building between 500 to 300. After that, no, it was burnt. Okay, but why conservation and restoration of cultural heritage? This is actually a common global topic because this is the history of mankind, and obviously we have to know our past to build a better future. So we need to define some consolidants to save the artifacts, human artifacts, and the integrity of cultural heritage. The fact is that artifacts and monuments are continuously degraded because of some natural phenomena like rain or pollutions, and also natural disasters like earthquake, like flood. So it's important to find proper consolidants. This issue, I mean, conservation and restoration of cultural heritage, needs actually an interdisciplinary team that knows architecture, they know history, nanotechnology, material science, so that we can preserve the structural characteristics of a building while we do not disturb its history or its architectural aspects. Quite recently, the use of nanotechnology in restoration and conservation of cultural heritage have been tested. And you could see, for example, in the picture, a painting that was actually restored, and it was actually cleaned through nanoparticles, and also a church that was restored with application of nanoparticle solutions. If you take a look at the publishments regarding nanotechnology and cultural heritage, you could see that it is quite increasing. It means that the attention of a scientific community to this topic is actually increasing. Also, the analysis of the Scopus shows that Italy is the leading country. Yes, yes. Is concerning the number of publications regarding the issue of nanotechnology and cultural heritage during different years.
But they are not classified within the different areas. Generic.
Yes, they are general. Yes, they are general. And this is the analysis from the Scopus that you can search by putting nanotechnology and cultural heritage, and gives you some analysis regarding the documents related to each countries, and also even the funding sponsors. And you could see that Italy is actually the leading country. That is because the enriched culture it has in this topic, and also it's actually because the funding policies that are more dominant in Italy. Okay, so what is nanotechnology? Nanotechnology is the design, characterization, production, and application of devices at the nanoscales. We call a material nanomaterial when at least one of its dimension is in 1 to 100 nanometer. And a lot of different properties occur in nanomaterials because these reduce dimensions. For example, non-transparent materials becomes completely transparent. This is useful, for example, when you want to coat a surface in conservation of a cultural heritage, but you don't want to disturb its appearance. Or for example, non-conductive materials become conductive. This is the case when you want to, for example, use the nanomaterials as sensors, as smart sensors. Or a material like gold, which is completely non-reactive, and that's why we can wear it every day. It becomes completely active or even a catalyst in reactions.
Yes. What is non-reactive?
Here we want to say that why we talk about nanomaterials, why nanomaterials is important. It is not just because the size is small. It's also because that a lot of properties differ when we change from macro scales to nano scales. For example, we have some material like gold that's in macro scale, it is actually non-reactive, so it's used as a jewelry. But when we are talking about gold nanoparticles, it becomes completely active, and even it can accelerate a reaction and being a catalyst. Okay. But how small is nanometer? When we say nanometer, what do we mean? Very small. 10 to the power of -9 is a nano. Okay, to have just an idea, a human hair is about 5,000 to 100,000 nanometer thick. Or if you, for example, compare a nanometer with a tennis ball, it is like comparing a tennis ball with the Earth itself. I also found this interactive image interesting, if I can bring it, of course. Okay, it starts from the actually Milky Galaxy. Okay, let's start from the Earth. It starts from the Earth, then we have the continents, we have the state, we have the city, houses, a bunch of trees.
Are you a student of the house? You cannot say. Yes. That make a noise.
Then we have a bunch of trees, we have a bunch of leaves, and this dimension that is written below the edge is actually the dimension of the dimension that you can see. So this is a leaf. We come closer, and we have not yet entered into the nanoscale. We have the leaf cells, we have the nucleus of the leaves, but it is still 1 micrometer. And here we have the formation in the leaf cell, and it is 100 nanometer, and it is actually the upper scale in nanotechnology. It is where we just enter to the nanotechnology. And then we have DNAs, and also we have atoms, And here it is in the order of 1 nanometer. Each single atoms are in the order of 1 nanometer, and it is the lowest scale of nanotechnology. After that, of course, we have subatomic scales, but we do not go through subatomic scales. But in nanotechnology, we usually use the data from subatomic scales, but use them in larger scales. So I hope that now you have an idea of how small nanometer is. So what are the functionalities of nanomaterials that make them good candidates in conservation and restoration of cultural heritage? The first one apparently is because they are so small. So for example, they can penetrate deep into the damaged artifacts and damaged areas. So they can fill the cracks. And for example, if you have a crack here, the water may insert in the crack. Even if it's very small, then it may get freeze, it may expand, the crack will, propagate, and little by little, this small crack may lead to a larger one. But when you can fill this space with nanomaterials, so no entering of water and no propagation of crack because of pollutions. So the first property that they have is that they can penetrate deep into the surfaces even when we have small cracks. Another important factor of nanomaterials is that they can create a transparent, when you apply it on a surface, they can create a transparent and self-cleaning layer. So what does it mean when we say self-cleaning? How can a surface be self-cleaned? Do you have any idea?
When the particles of the painting itself got cleared, like in what can I say? I don't have anything.
It's okay.
Like the particles of painting, cleaned, but not measured. They itself got clean those chemicals.
So how they get clean?
With nanoparticles inside.
You mean that the nanoparticles is live, so they clean the surface?
Yeah, they itself clean inside in layers.
It can be a good actual idea, but right now it's quite simpler, on the whole, self-cleaning, I'm just going to talk a little about self-cleaning because it's actually one of the most important characteristics of applying nanoparticle coats on surfaces. We can have different mechanisms in self-cleaning, and actually comes from a natural phenomena, what we have in lotus. You know that in lotus, when you pour the water forms like individual drops. It doesn't spread on the surface. So it means that when the surface cannot be wet, it cannot absorb dirt. And on the other hand, these spherical drops can easily roll away, so they can move the dirt out with themselves. So one of the functions that nanomaterial is that we call this characteristic hydrophobic. It comes from hydro, which means water, and phobic, which comes from phobia. It means that the surface do not like water and it repels water. So some nanomaterials causes the surface to become hydrophobic, or actually super hydrophobic, so that the water cannot stand on them. The nanomaterials that are used for this purpose are usually metal oxides or metals, and they can be applied, and they are actually successfully applied on wood, on paper, limestones, and also marbles. Another mechanism for self-cleaning is actually opposite hydrophobic, super hydrophobic. It is super hydrophilic. It means that it likes water. How it happens? When the surface likes the water easily spreads on the surface, so it can easily wash away the dirt. So we have two extents of self-cleaning that both of them can work. And less nanomaterials like silica nanoparticles can be used to make a surface super hydrophilic. Make a surface super hydrophilic. It means that the surface likes the water so much, so that when you pour the water, it spreads on the surface and it becomes completely clean. So the drops will not remain, and we have a mechanism that it washes the surface. Here we also talked about super hydrophilic. hydrophobic.
For most phenomena are because of the nanoparticles.
Yes, because of the, it's not that just with nanoparticles we can create this. Some materials like silicon, they themselves has the hydrophobicity. But with nanoparticles, we can produce these features super actually hydrophobic or hydrophilic. Yeah.
And I think those products are like waterproof. They have this.
Yes. The hydrophobic one is completely like waterproof. It's actually what they do in other industries too. And the last one, it is photovoltaic, and it is usually is a characteristic of titanium oxide. And titanium oxide has a very actually interesting mechanism. When it's also sometimes used on the glasses. When it is applied on the surface and the UV radiation is applied on the surface, it produces some electrons, and then the electrons actually disturbs the dirt. They break the dirt, and also gives the surface a hydrophilicity. So then when the water comes, it washes the dirt completely. So the dirts are also disturbed, and then they are washed through the water. So it's so effective, and it's one of the nanoparticles that is mostly used for self-cleaning surfaces. Okay. You can ask any question.
I said that because of the noise.
Oh, it's okay. We apply titanium oxide on the surface. Okay, so it becomes photocatalytic because it is actuated. It is reactive using photo. It means the UV radiation, like the sun, reflects on the surface. Then it produces some electrons, some radicals that they can interact with the dirt. They disturb the dirt. And then when the water is applied, and it disturbs the dirt and also make the surface hydrophilic. So they like the water. So when you pour the water, you have both the dirts are actually, disturbed. Yes, the dirts are disturbed, so they can easily move out from the surface, and the surface is hydrophilic. So the water is spread out easily on the surface, and it's completely clean. Okay, so there are some kinds of other nanomaterials that we have, both metallic oxide and metal nanoparticles, that they can, you can see that some of them give self-cleaning to a surface, and some of them, for example, gives hydrophobicity, but also they can actually have a UV protection effect to the sun. And we have also protection against microorganisms. It is also one of the important usage of nanoparticles. They make the surface antibacterial, they make the surface antifungal. And okay, another important features of nanoparticles is increasing mechanical strength. You know that usually masonry materials are brittle, they can easily crack. But by adding even a very small content of nanomaterial, you can increase the stiffness while you can increase the elasticity of the material. Okay, for example, just as an example, I have brought a figure that you can see. We have a cement before and with nanoparticles, and you can see the compressive strength has increased by adding nanoparticles to the cement. So, of course, for cultural heritage, we already have the building. So we use nanoparticles to make polymers, or also cement reinforced nanoparticles to apply to the areas that have cracks, so that the cracks are filled and we have much stronger materials in those parts. Also, it is shown that soluble salts, when it's present in the stones, it will decay the material properties. One of the functions of nanomaterials is that they desulfate. There are some of them are desulfating agents, so that you can apply them and it will desulfate the material and make it more stable mechanically. Okay. One of the other nanoparticles is hydroxyapatite. Hydroxyapatite is actually an inorganic mineral that naturally exists in human body, in the bones or in the teeth. And it has the main role for structural strength of the bone and also bone regeneration. Okay, do you know what do we mean by bone regeneration? Oh, it means that a student, I think, at the end of the bone regeneration is the process that, for example, when the bone is hurt, of course the bone is still live, so it can reproduce itself. And one of the materials that is needed for this process is hydroxyapatite. But in a structural masonry, of course, we use it as a consolidation. We use it as something that makes it strong, the limestones, marbles, and chalk stone. And because it has low viscosity, you know what is viscosity? For example, in comparison of water and honey, yes. Honey is more viscous. When you, for example, want to pour it, water pours so much easily, but honey is thicker. Okay, so when a material is viscous, it means that it can easily pour and penetrate in different surfaces. Okay, so the aqueous consolidants of when we combine it with water, hydroxyapatite becomes it has low viscosity, so it can penetrate easily in the cracks, and then it can improve the mechanical properties of the stone. And that is why you may hear that this is much used for strengthening stones and construction materials. Also, it has been seen that if you add this one with gold and apply it on surface, it gives hydrophobicity to the surface. So it also has that self-cleaning mechanism. Okay. But usually the works that are done on cultural heritage and nanomaterials focus on using nanoparticles, as I told you, metallic oxide or metal nanoparticles. But we have a very interesting nanostructure that is carbon nanotube. You may have heard the name of CNT or carbon nanotube. It is a tube that is made of, all the elements are made of carbons, and its diameter is in the range of nanometer, 1 to 100 nanometer. We can have a single carbon nanotube. You know, it is not actually built by this. Have you heard about graphene? It is a nanoplate actually that is made just by carbons. We have carbons that make hexagonal lattices here, and carbon nanotubes can be considered as a graphene layer that is rolled into a cylinder. Of course, it is not really made by this. You know, we have very special methods to construct carbon nanotubes, but we can consider that it is actually formed by rolling of this graphene sheet. And we can also have multi-wall carbon nanotubes, which is nested single-wall carbon nanotubes. And since it has been discovered in 1991, a great attention has been devoted to carbon nanotubes. If you can just make a little search on carbon nanotubes and the publications that are about it in different areas, you know, not only mechanical and thermal, electrical, optical, and also biological. And because it has, you know, very special properties. For example, its Young's modulus, are you familiar with its stiffness, is about 1 TPa, which is 5 times of the steel, for example. And it can be used in different areas, like it can be used as nanospring, it can be used as nano-oscillators, sensors, because it is electrically conductive. So for example, if you can build a relation between its length and its electric conductivity, then it can, when the length changes, the voltage that it induces changes, so it can be used as a sensor. Okay, it can be used as a sensor. And okay, we will talk how this property can help us in structural monitoring. And also a very famous characteristic is as nano-reinforcement elements. For example, you can see that when we use carbon nanotube in a cement, even very small number of carbon nanotube in the cement, if this is the damaged area in the cement under an applied load, by applying a small number of carbon nanotube, the damaged surfaces are really changed. Or, for example, schematically shows that when you have a cement reinforced by carbon nanotube, how it sometimes acts like a glue and binds the. If it's in the polymer, it binds the polymer chain. If it's in the cement, it binds the cement particles together. So it hinders, makes hard the crack propagation. Also, as I told you, it can be used as a sensor. So we can use it in cements, and then the cements will have a self-sensing property. Okay, so for example, if we use it as a repair material, we have a cement reinforced carbon nanotube that is the stronger, and also we have given it a self-monitoring property. For example, here you could see that, of course, honestly, I couldn't find anything about health monitoring of cultural heritage using carbon nanotubes. We have some papers that's about carbon nanotubes and structures and cements, but not about health monitoring. I just made up this picture myself. For example, one of the things that we can do is to, this is one of the type of the works that I do, as I told you, I do atomistic simulation. It's actually a bulk of material. This is cements, and this is a carbon nanotube. We, for example, simulate the carbon nanotube inside a cement. We find the material properties, and also we find that, for example, then at what scale, how much should we, for example, elongate this cell so that the cement starts to break? So that we have a calibration between the magnitude that we elongate this material and the crack inside the material. So we can actually monitor. Then, for example, if you apply it on different parts of the cultural heritage, you can monitor the state of stresses and strains and whether the stress has caused the crack in the material. So we have given it a health monitoring ability, and actually also reinforcing it by the type of cements that we have used. As another big topic that we are interested to work on is to analyze a building, a cultural heritage building, and find the weak points and the points that are more prone to be cracked. And then we can modulate actually depending on the size of the nanotube that we use, depending on the content, how much it is concentrated. And even the orientation of the nanotubes can change the difference. In this block, it is different. What is the orientation of the nanotube that you are using here? So it gives it directional properties. So we can modulate the carbon nanotube in different parts. We have strengthened the weak points. We have also filled the cracks, and we have given it a structural monitoring ability. Okay, and so soon. These are the references that I have used for this presentation, and thank you so much. In case you're interested for the next course that is conjugated with this course, Atelier of Structural Masonry, this can also be a topic. Of course, qualitatively, we are not going to work in details or simulations, that you can work about nanotechnology and cultural heritage. Thank you.